It's been a while since I posted a video about PID tuning using Betaflight and PID Toolbox. So what we're going to do today is a sort of rapid-fire Betaflight PID tune using one, maybe two packs, focusing on the main things in PID Toolbox that will help users of all levels make significant improvements in flight performance. First thing we're going to do is plug in our drone. We're going to go right down to the PID tuning tab. Everything here is basically set up on stock, but in order to do these tests, we are going to use angle mode. That makes it easier to do, and we're going to be using the auto wobble script that I've shown in a previous video how to implement into an Edge TX or OpenTX radio. So in order to do that, we're going to want to drop our angle limit down a little bit. By default, this is much higher, so we're going to drop that down to 30. And the second thing we're going to do, we're going to create, let's call it a tuning rate profile. In Betaflight 4.5, the shape of your rate curve actually impacts angle mode. So what I'm setting up here is 150 across the board for center sensitivity and a max rate of 150. When these two numbers are the same, you get a linear rate here, and that's going to make it much more manageable. So literally I could do this in my basement or in a small confined space. Fortunately, we're out here in the field, so it's not going to matter too much. I should mention that when you have your rates set up like this as well, you could technically do this in angle or acro mode, so that's your choice. Otherwise, we also have our filters set up here, so this is all stock filters to start with as well, okay? The first thing we're going to do is a steady hover. Why do we want to do a steady hover? There's several reasons. A steady hover gives us a spectral output of the drone under ideal conditions without any user input or external influences like wind, etc. Those things are going to influence the spectrum as well. And it turns out that it's a really good way to assess whether you have any electrical or gyro issues with the drone. If you have any of those issues, you're going to want to resolve that first. Then we're going to go down to black box. For Betaflight 4.5 and later, you're going to want to set the debug mode to FFT_FREQ. Don't worry about that for now. Just know that that's going to allow us to see the activity of our dynamic notches. We don't need to use gyro scaled anymore because the pre-filtered gyro is always recorded in the log file since Betaflight 4.5. So we're just going to bring the drone up into a hover, hold it steady for about 30 or 40 seconds. So that's the first test. We always do that. Let's take a look at it. We're going to go to black box, activate mass storage. We're going to call this steady hover, whatever, doesn't matter. We're going to go into PID Toolbox, hit open file, steady hover. Okay, so this is a clean build, so I'm not too worried about it. If you wanted to crop some of this, you could crop it, but really there's not much to look at. As you can see, across roll there is the set point in red, the gyro behind it in white, roll, pitch, yaw, and down here are the motor sigs. All we're going to do is go to the spectral analyzer, plot the pre and post filter gyro. That's the default that you have set up in the spectral analyzer. We're just going to hit run on that. Okay. What you're looking at here is the pre-filtered gyro is the dotted line and the post-filtered is the solid line. That's for roll, pitch, and yaw. And over here is just the zoomed in version of that first 0 to 100 hertz. If we just plot the RPM harmonics on top of this, we'll be able to see what part of this noise is related to the motors and what part is something else. You can see that this main peak of noise here is from the first motor band. That's what these lines represent, the motor RPM. And then here's the second, so you can see there's not much sitting underneath the second, so there's no real second harmonic. And there's the third. So you can see that the first and the third are the main motor peaks, but there's something going on here in the middle between the first and second harmonics. So these are what we would call resonance peaks. So we're going to need to use dynamic notches to address some of that. RPM filters are working really good as they are, as we can see, and we don't really have much of a second harmonic. Ideally, what we want to do with filters is use only the amount of filters that we need. So I'm going to drop gyro low pass 1. If we're going to drop one low pass filter, you want to turn off low pass 1, not low pass 2. And we are going to increase the number of notches to take care of the resonance peak that we see on roll. So we're going to up the count there to 3. Now to compensate for that, we're going to try to reduce some filter delay associated with the RPM filters. Since we don't have much of a second harmonic, we're going to reduce the filter weight. We're going to talk about filter weights really quickly. You're just going to go into CLI, and if you go get space RPM, you'll see it populate all of the things that are associated with RPM filters. So we're going to look at RPM filter weights. Just click on that and hit enter, and you'll notice that the weights here, it says RPM filter weights equals 100, 100, 100. This is a percentage of effectiveness, let's say, of the RPM filters. So we're going to go set RPM filter weights equals 100. We're going to want full strength of the first harmonic, and we're going to go about 25 for the second because we didn't really see much happening there. And then we're going to set the third at 100, and then we're going to type save, S-A-V-E, and enter. Okay, so that's already going to reduce some filter delay, and we're going to need that because we have to offset the fact that we had to use more dynamic notches. We're going to do one more quick hover test and make sure that things are looking okay. So you know, it's kind of interesting that even with the hover test, we were able to see that we have this issue on roll. So it kind of proves the point that you can get a lot of information from a simple hover. All right, that's all we need. Let's go into black box, steady hover, new filters. Okay, so you know, if we go back to that first one, you can actually see that issue here. If I actually plot the D term that's in yellow, you can actually see the issue. So there's the issue that we're seeing, right? It's kind of obvious to me now. So it's important to look at the raw data, and when you plot the D term, it'll usually accentuate where the problem areas are. And so you can see that resonance is showing up at different points in the hover, and you can see it as well in the thickness of the motor, commanded motor signals. And so now when you look at the new result, you can see that that's pretty much gone, right? So our dynamic notches have to be working. So we're going to see that in the spectral analyzer. You can see that it's starting to work on those resonance peaks here. Let's see what it's costing us. Go to the delay drop down, click filter delay, and you can see we're at 2.0 on the gyro. So that's pretty good. But what we're going to do, we're going to try to drop that filter delay even more. I think we can get that well below 2 milliseconds. So we're going to go back into Betaflight. I'm going to widen these notches a little bit. So that first resonance peak doesn't start till after 160 hertz. We're going to raise the minimum frequency of the dynamic notches to 150. I'm actually going to drop this down as well. This is going to constrain those notches in a smaller area, and we'll widen the Q factor a little bit. To offset that cost, we're going to go into CLI, and I'm going to go set RPM. I'm going to raise the RPM filter Q factor. By default, the RPM Q factor is set at 500. Simply raising that to about 1,000 will save you a lot of filter delay. Okay, so I think we're in business now to start tuning. So let's go back to our PID tuning tab. So the way I decided I'm going to do this is I'm going to use the Betaflight OSD in the goggles. So I'll be manipulating the PID sliders in there. This allows me to do a series of tests without having to come back and forth to the computer. But before we do that, we have to make a few adjustments in here. So the first thing we're going to do is, these are the default slider values. We need to set this up for PID tuning. Now, I've mentioned in many videos before, the tuning process is basically three steps. And the steps revolve around the idea that there's a relationship between the PID terms. So there's a relationship between P and D, and we want to optimize that. We'll call that the PD balance or the PD ratio. And then there's a relationship between P and I. So we're going to want to optimize that as well. And then the master multiplier. So the two metrics we look at are overshoot in the step response and the latency of the step response. Those are our two metrics. So step one, we're going to optimize the P to D ratio. What we'll do to do that is we're going to manipulate the damping slider. So we're going to start that down at about 0.6. We're going to leave the PI tracking slider. We don't need that. We're going to take the stick response down to 0. We don't want the effective feed forward. Now, if you're doing this in angle mode in Betaflight 4.5, feed forward doesn't have any impact anyway, but I want you to get used to doing this for people out there that want to do this in acro mode. There's plenty of people who like to do that instead. So we'll drop that out. We're going to take the dynamic damping out because we don't want D turn to be a moving target. This will keep the D max and the derivative values the same. We're going to bring the I term down for now so that we don't confuse the impact of overshoot related to I term with overshoot related to a lack of D term. Those things can get confusing, and a lot of people make that mistake. So we bring the I gains down initially. We're going to bring that up later when we start to look at the P to I relationship. I also like to just drop the pitch damping down a little bit to match these numbers. You'll notice that by default, Betaflight has a higher D value for pitch than roll. That's assuming that there's a weight distribution difference between roll and pitch. I like to keep the two axes as close as possible for these initial tests, so we'll bump that to 0.9. And then the last thing is the master multiplier, where to start that. So for most drones, 5-inch drones, you can probably start with the master where it is at the default of 1.0. But some 5-inch drones, especially little racing drones, can be really powerful, and they're already overtuned at 1.0. So to avoid that issue with a high-powered rig, I would drop this down to about 0.8 or 0.7 or so, just for those initial tests. Yeah, and for larger rigs, it's sometimes the reverse, where you actually have to boost the master multiplier to start, because you're in a highly undertuned state, and it tends to make interpretation of the step response a little bit confusing. Okay, so we have our starting values. We're going to hit save on that. Now, I'm doing these line of sight, but you'll see the overlay of the goggles. Just note that. Some people do like to do these tests with the goggles if you're really not good at line of sight, but I encourage you to try to at least have some basic line of sight skills. It's not a bad idea. We're going to arm, put it in angle mode, and then we're going to bring it up. And when I'm ready and I'm comfortable, I'll just start the auto wobble script, and boom, here it goes. So you can see it's just continuing to go. As long as I hold this, as long as I hold the momentary switch in, it'll stay wobbling like that. I'll have a link in the description about how you can set this up on your Edge TX or OpenTX radio. I've got mine with a counter, so you can hear it in the background telling me how long it's been going. Okay, so that's enough. And then we're going to go in here and we're going to go profile, simplified tuning, and we're going to go to our D gains, and we're going to bump it up to 0.8. Go back, save and exit, and we're ready for test 2. So you notice it's not very aggressive. You can set, I've got the max angle set to 30 degrees. You could certainly make it more aggressive than that if you like. It's not going to really make any difference. All right. Profile, simplified tuning, D gains 1.0, back, save and exit. D gains 1.2, save and exit. Now the nice thing is we have all of those log files in a single log file. They're going to show up as sub-files basically. So sometimes that's kind of convenient to have it all packaged into one file. So this was our step 1, which was our PD balance or PD ratio, right? So we'll call those PD balance tests. So let's load those in. So we did damping 0.6, 0.8, 1.0 and 1.2. There's the results of our wobble test. We can just go into the step response, grab those 4 tests and run. So we're looking at roll and pitch here. We're going to ignore yaw, so I'm just going to turn that off. And you can see here, this is 0.6 in red, 0.8 in orange, 1.0 in yellow, and 1.2 in green. So you can see a systematic decrease in that overshoot. And clearly the 1.2 is even really over dampened. I think I would go with either the orange or the yellow. So 0.8 or 1.0 is fine. I think I would actually probably go with the yellow. The second thing I look at here is the difference between roll and pitch. Now, for a rig like this is a little 5-inch. It's a true X, and the weight is fairly evenly distributed across roll and pitch. So there's a little bit more weight distributed across pitch, but not enough to make a big difference. And you can see that here in terms of the response. The difference between roll and pitch is very, very minor. So I don't think I'm going to even bother to boost the pitch axis at all here. I don't think there's any reason to do that. Okay, so we're going to go back out of here, go into Betaflight, go to PID tuning. So again, I think anywhere between 0.8 and a 1.0 is going to work fine. I'm just going to go back to 1.0 because I think erring on the side of slightly more D-term is going to yield better prop wash performance. So that's what I'm aiming for. So I'll go with that. The next series of tests we're going to do then is with the master multiplier. Let's start at 0.6, save and exit, save and exit. Master multiplier, 0.8. So I don't hear any oscillations. You always want to be listening for any kind of oscillations during this. I know this drone pretty well, so I don't think there's a problem here, but keep an eye on that. So as you boost that master multiplier up, especially a drone that you're not too familiar with. We're going to go into PID Toolbox, open up the master multiplier tests. We did MM 0.6, 0.8, 1.0, 1.2, 1.4, and 1.6. Select all, hit OK. We're going to run the step response. Let's just grab all those tests. I like to use the cross-correlation latency here. I have other videos where I describe what that is, but don't worry too much about it. Just know that there are two ways of measuring latency. Both of them should correlate, but sometimes this one is the bit more accurate one. And the metric we're going to look at with respect to the master multiplier is latency. So you can see our series of tests here. You can see a beautiful drop in latency. You can see it start to take a sort of curve where it's starting to plateau. And you can see the same on the pitch axis as well. But notice over here, if we zoom in on those curves, you can see that one of them is clearly oscillating, right? So you can see the same thing happening on pitch. So that's the highest master multiplier. That was the 1.6 setting. So we're certainly not going to go that high. So let's go back and just plot 1 to 5 now. And then you can see even that fourth one, so the master 1.4 is starting to ripple. So we're going to go back one more even, reset and run. Still a little bit of a ripple there, but that's not an oscillation per se. So, you know, I would probably go with the master multiplier at about 1.2 here. So we are at our sliders again. So we're gonna go with the 1.2 on that. Hit save. And the last thing we're going to do is we're going to do some I-term tests. Oftentimes I say I-term has a very wide tuning window in that you don't really need to worry about it. With a 5-inch, you could literally just bring that back to 1.0 and it's good to go. But I want to show you what the PI ratio does to the result. I think what you're going to find is that especially because this drone is really tiny, we're not going to notice any difference as we increase I-terms. So you might be wondering why we do the PI balance tests after the master multiplier. And the simple answer to that is when you do the master multiplier tests first, you collapse the PID error that's generated because of the delay between the set point and gyro. And so I-term is less likely to wind up. So what you're looking at here are the results of a series of I-term tests. So this is where we varied I-term from 0.5 in red to 1.0, 1.5, right on up to 2.0. And as you can see, there's no difference in the step responses. So there's clearly no issue with I-term winding up or generating any extra overshoot or anything in this case. And that's simply because the rig is so light that the PID error is really low and there's no opportunity for I-term to accumulate. So I think in the end, we're just gonna set I-term back at 1.0 and then bring the feed forward back at 1.0, and I think we're going to end the tune there. So let's take a look at Betaflight. So here's the final set of PIDs that we decided to use, and here is the final set of filters.